All right, Hacksters. Today we have an awesome chat lined up for you. We have Sean Cross, who you might know from various projects such as the Omus, Tomu, Fomu, etc. There's a Bluetooth one now, right?
There is. I think it's called Bomu, Womu, something like that.
And also the Be Trusted project. And I've heard about you. Like, it seems like every once in a while I'll interview someone else and they'll be like, oh, but you should really talk to Sean about that. He's the one who really did all the masterminding. I'm like, oh, I gotta get Sean on the show. So I'm so excited. How are you, Sean?
I'm great. How are you?
Marvelous. And I have to say, your voice sounds very mellifluous over whatever audio setup you have there. It's so good.
Thank you. No, it's it was still in the middle of COVID, and Singapore actually locked down in March of last year. And the thing about Singapore is our houses tend to be very small. So my house is, I think it's 636 square feet when you do the conversion, 64 square meters. And it is very noisy here.
Ooh.
And over the course of lockdown, because we were doing a lot of video conferencing and everybody's working from home now, I decided to go out and purchase this headset, which is really nice. And it comes with this nice little soundboard thing.
Oh.
Um, and also, using NVIDIA has some amazing sound processing software that's cutting out all of the traffic noise and things like that. So thank you. It's nice to know that's paid off.
It really is. It sounds great. I have a question regarding sounding great. Your nickname is XOBS. Do you say Zobs?
I do. That's how I tend to pronounce that. Yeah.
And where does that
Uh,
come from?
it actually comes from college, from university. I went by a different name that was based on my initials, just online, and I wanted something that was more unique. And the story goes, I was actually in a cryptography class, and they were working on substitution boxes, and I thought, reversing things is kind of a form of encryption. So I liked the name S box, and so I just swapped it around.
Ha ha
Uh,
ha ha ha.
comes up Zobs, yeah.
Brilliant.
Uh, yeah, and actually, the first time I used that name was so I used to work for a company called Chumby. They
Yeah.
were probably one of the first major open hardware companies since the early 80s. I mean, you could actually get the schematics for the device, which was fairly unique at the time. And I joined as a tester initially. So I was doing testing on the firmware and operating system. And one of the founders of one of the early employees and one of the people who designed the Chumbe mainboard was Bunny Huang, who I believe you've had on your show previously.
Yep.
And um, we had some downtime in between boards there, and they used to sell what they called an open source picture frame, or Linux based picture frame,
Oh
which
yeah.
was a Blackfin based device. And it turns out to be fairly simple to get SSH access to that. And so one time during downtime, I ported the whole Chumby Flash player to this board, and went and showed the execs. And I guess they were just like they were flabbergasted. Like, how did this person from the testing department do this when we were actually looking at porting to a Blackfin possibly? And they said it would take a couple of months, and
Bah.
this guy did it in his spare time. Um,
They were
that
probably
is when
giving
I,
your standard like double time estimate, right?
yeah, well, it's what they say, double it and increase the number, right? So if it's going to
Mm,
take two hours, it'll take 4 days.
right, yeah.
Um, and to be fair, this thing did have all sorts of issues, but most of the problems in that was uh, ARM CPUs are a bit different when it comes to various integer sizes in C++, and it gets really weird.
Huh.
Um, but I did manage to get that successfully ported. And that was when I first encountered Bunny. That basically made him recognize me as as somebody who could be valuable in the firmware department, and that is kind of what started me doing firmware development from that point on.
That's
Um,
awesome. And
and
you've since worked together on lots of things, right?
Right. So I mentioned the story because it was actually Bunny the first time who used that name on one of his blogs, uh, describing the port I did of Quake to the Chumby, which was also a tech demonstration because that was basically recompiling everything using soft floats because there's no floating point on that.
Hmm.
Yeah. So, sorry, you had a question?
No, that was the only question. Actually, I have another question, which is that I see you have a poster from a museum that I went to, which is the Museum of, is that the Museum of Soviet automatic like arcade machines?
Yeah, it is. Well, you actually went there. Wow,
I
cool.
went there. That's so cool. And I loved this poster. I almost got it.
Uh,
What's the story? Why do you have this poster?
so this actually comes from the first time from when I initially met my wife. So she's Singaporean, and we went together on a trip to Germany and Belgium, and eventually to Russia in 2012,
Huh.
December 21st, 2012. End of the world. Um, I we all went to Belgium, and then I went to CCC in Germany, and she went and saw some friends, and then we met up together in Russia.
Hmm.
So that was when we first got together. We are kind of, none of us even read Cyrillic, which is kind of a requirement when you're in Russia. And we just had no idea what to do. And actually, one of the
Oh
people
no.
at the hotel recommended, hey, there's this museum. Like, what? um, and do they still have the online version of the museum? They used to have
Oh.
flash versions of, well, this game actually, the one on the poster, which it's kind of a scary, like just because there's this big disembodied face on the screen who's saying Russian things at you. Um, but it's yeah, no, it's a racing game, and it's a stand up cabinet with wheels on the front. I don't know how if you could see that. Um,
Ah.
but yeah, we decided to go to this museum and liked it so much that we bought the poster, which this poster is, I believe, an A0 size poster, which is a huge pain to get back.
Uh-huh.
And it's impossible to find a poster frame for it. So this one is actually just laminate with like black tape on the corners.
Ah,
Um,
nice.
yeah, it's a great poster.
It's a great poster. On to things that you have made. So back in December, part of the reason we had Bunny on was to talk about Precursor. And as you were just mentioning, it is a precursor. It's called that because it's a precursor to Be Trusted. So first off, congratulations. You finished at about twice what you were asking for on your goal. That's so cool. And what's it been
Thank
like?
you. Um, it's been a challenge. So the reason why it's called Precursor, and there's actually a bit of confusion here because there are two different projects. There is Be Trusted and there is Precursor. And Be Trusted is still in the planning department. It is going to be a secure chat device. So this is going to be a device that is guaranteed free from any sort of snooping, completely inspectable. It's going to probably be a matrix client, and it is going to
Hmm.
be something that you can just take out, tether to your phone or your home Wi-Fi or your wherever, and securely communicate with anybody who is also on Matrix. At least you can be verified that if you've exchanged private keys, you're talking to the correct person and they haven't been man in the middle due to a hardware bug or anything like that. That is a product, but it also requires a lot of validation. It requires an operating system. It requires hardware that's been tested. And so, in order to validate that is all working and to provide people with something today that they can
Huh,
hack on, we came up with Precursor, which is the precursor to the Be Trusted product.
I
Now,
see.
they're all going to be open source. They're all going to have a common um, uh, source repository. But the issue is that Precursor does not have a well-defined uh, operating system or even programming method. So
Hmm.
what you're going to get is you're going to get the system as it is in its current state, a system to program it, and a working hardware that has been tested, gone through FCC validation, for example. You're going to get everything on the
Mm,
website, but the software is not necessarily going to be there. You
I
can't
see.
take it out and use it as a chat client right now. But we do have hardware. So this is what it looks like.
Ooh.
This is running an early version of the software. So you
Ooh.
just test firmware, to test to make sure that the keyboard works. You could press keys,
Huh.
and what this is a version without. Unfortunately, it's really really tiny. Interesting thing, you can see here that there's this really nice artwork on here,
It's beautiful.
and this artwork I believe was done in Illustrator. Bunny can tell you more, but I think he did it in Illustrator and imported it into Altium, because this whole front piece is actually a PCB, and it's
Oh,
designed so that if you want your own, you can just go to your local PCB shop. You know, if you're afraid that, for example, this PCB has, I don't know, a chip embedded on an internal layer, which is a thing they can do now,
oh,
um, then you just go fabricate your own one, and you don't have to trust that the supply chain from us was validated. You can go to Osh Park or someplace like that and actually follow the PCB as it goes through its production. And then you can be guaranteed that there hasn't been some supply chain disruption where they've swapped it out with a different board that has something embedded on the inside. That's the sort of defenses that Precursor and Betrusted are looking to build in order to avoid the sort of interception that is possible.
amazing. And who is your target for this? So I can see, for example, journalists may be using this if they really need to communicate securely with sources or things like that. Who are you thinking of?
I know, again, this is mostly Bunny, but I know his target market is exactly that: journalists who are in potentially hazardous areas where there is a very real risk of state interception or otherwise something that can endanger, if not themselves, and their sources as well. So you definitely want to be able to have a secure line of communication in the field without, for example, at the border, having a border agent go take your phone and add a bug or something like that at the
Right.
point of border entry, uh, uh, which again is another thing that is definitely can happen. So the idea behind Betrusted is you can guarantee that they're not going to plug it into a machine that is going to suck out all of your contacts and all of your chat history,
Mm.
and also not going to install something on your device that is going to then start relaying all the information back to them, or even the super micro incident that Bloomberg reported on. That's you know
The grain of rice thing?
the grain of rice probably doesn't exist. Uh, but the idea is this would be something you could use to guard against even that.
Mm. So one more question. You showed us that really fancy, pretty version, and I noticed that it had a little rectangle that was kind of incongruous with the visual design. You've also got it on this plain
Yeah,
version. Yeah,
yeah,
is this like a touch? Oh, it's got a little lock on it.
yeah. I mean, I guess it's a touch in the sense that the iPhone 4, if you touch the side, it would disconnect. That's an antenna. So this is an actual
Oh,
linked match, impedance matched antenna um, that is part of the PCB, because you can either use a chip antenna or a strip antenna or something like that. But you can just do it on a PCB if you length match it properly. And that's what that is. Um,
cool. So
yeah.
your story. You came to Chumbi and you wowed everyone with being able to port this thing to the Blackfin just out of nowhere. And so, where did you come from? How did you get to that point? Are you self-taught? Did you go to school for something? Both?
Ah, it's an excellent question. So I went to school, I went to university. I applied during the dot-com boom, year 2000, and I got in. But they did this really interesting thing where they said, "You're in school, great. You're in UC San Diego, but the major you applied to, computer science, that's a no-go because everyone wants to do computer science, and we're not going to let you in there. Additionally, you can't do computer engineering, electrical engineering, or mechanical engineering.
What?
You can pick anything else." I'm like, well, okay. Um,
Well, horse riding then.
well, I chose brains because I figured
Oh,
cognitive science, it's kind of like, squishy computer. You're never going to use any of this neuron stuff. Like that's so like orthogonal to computer science that, it's going to be just kind of a nice another way of computing, but that's never going to be useful in computer science ever. And so I did cognitive science. and everything computer and electrical engineering has been self-taught. I have to thank my parents. I was very fortunate that when I was growing up, we always had some sort of computing device, either a Commodore 64 or an Amiga. So that really got me into computing as a young person. But for training, it's mostly self-taught, making lots and lots of mistakes.
Yeah.
Lots of destroyed boards with going crazy with a soldering iron. Um, Getting better, but it's still 50% chance that the thing will actually work.
Mm. Well, pursuant to that, I found a couple of awesome tweets of yours, not to highlight the mistakes, but it is cool to see the failure modes here. And
Yeah.
it seems very real in the manufacturing sphere. So we've got these guys. What was happening here?
So for this one, so this is Fomu. This is one of the initial builds of Fomu, and I love it. Looks exactly like somebody took an erase tool to these.
It really
Uh,
does.
so so if you look, I don't actually have any panels anymore, but so, on the left and right sides, you can see what are called mouse bites,
Hmm.
and in fact, the bottom middle two still have their mouse bites on the right hand side. What they do is when they panelize these, there are, I think for this one, there were 20 to a panel, and they need some way to pop them out. And the problem with Fomu and Tomu is that they're 0.6 millimeters thick.
Ugh.
And so if you pop it out, there's a very real chance that you'll actually pop the components off.
Ooh.
And so what the factory decided to do was instead of popping them off, they would actually train a CNC drill and a special
Oh.
jig to go and cut them out. And needless to say, it missed. Um,
Needs more
I don't
training.
know why it missed 8 times. I don't
Did
know
you
why
have
the
like
guy just.
eight panels and like it, or it seems like such a, because those ones on the bottom and the one in the top right, they're very clearly a single failure continuing happening like over and over. It's so
I
strange.
think this was one panel. They ran one panel and then did this, and um, yeah, it's so sad.
Did they at least send you replacements?
Um, no, and that's one of the problems with manufacturing, and that's why uh, when you see that there's the BOM cost, the bill of materials cost for components, including the PCB, and then there's the cost that they sell uh, at the storefront, and those are all very different, and that is to cover problems like this that always crop up. Something always goes wrong. Fortunately, it's usually only one or two things, um, but something always goes wrong, and you have to cover the costs for those mistakes. Um,
It's really interesting to me that those costs fall on you, but yeah, I guess that's business.
yeah. Um,
There's another one here. I wasn't specifically picking out failures, but I thought
Failures are
it's
interesting.
interesting to, right? Yeah. So what happened here? Is it the shipper or
Um,
what do you do in
no,
a case like this? You just sort of go on with what you have?
so this one, damage in transit was entirely on me, um, because we didn't have enough. Um, I don't have a packing
Oh no.
facilities here, so I have to pack everything by hand. And I was
Right.
reusing the red bubble wrap that you see there. And the story with these boards goes. Um, Let me see if I could find the data sheet, uh, because uh, the way these things work is you look at the data sheet and you have to create the footprint in your CAD software, and uh, then what you have to do from that point on is get it produced and then solder the thing down. Now the problem was that, so this is the data sheet for the crystal that's on Fomu. And you can see they have this picture right here, pin 1, pin 2, pin 3, pin 4, and then they have the footprint, pin 1, pin 2, pin 3, pin 4, except this is a bottom view and this is a top view.
Hmm.
And this kind of mistake happens all the time. And I wish I would have caught it, but I didn't. And so I built the pad backwards.
Oh no.
And so we fabbed out. Fortunately, it was only about 30 boards, but this board was fabricated backwards. And that means that the crystal didn't crystallize, didn't oscillate. It didn't do what it was supposed to do. And the thing is, with USB, you need a very precise crystal within, I think, 1% accuracy, which means you can't use an on chip oscillator, RC oscillator.
Mm.
So we needed that crystal to work. And what I was going to do was just scrap all of those boards. But I decided at CCC to instead give this workshop and just use all of the scrap boards and treat it kind of like a rework project. Here is 30 boards that have been reworked. They might not work. They might because I didn't have a proper soldering station at the time. If it does work, great. You can come and do the workshop. If it doesn't work, you now have a soldering project. um,
And are these the same as this other board that's for testing the RGB LEDs on the
oh
Fomu? It looks very
no.
similar, but maybe not.
Uh, so that's this guy, which you have right there.
Hmm.
This is electrically identical to uh, this. So this is
Oh
Fomu,
wow.
Fomu, and this is what I call EVT. So this is what we shipped in production, and this is what I did the development on.
Huh.
So this has a much bigger FPGA. That's the FPGA right there,
Mm.
which you could see is bigger than Fomu itself. Like if we use this FPGA, then we would have no room for any other components. And the thing is, it's the exact same bit of silicon on the inside. It's just one is a bigger package, and the
Huh.
other one is just much more difficult to solder. So it's kind of a trade-off. Do you need something that's super tiny if you're putting it in like an iPhone, or is it okay to use a bigger package that you're going to have less yield issues for when it actually comes time to solder it down? Um, so I went with, for the development board, the big one, because again, this is much easier to work with, and it could put actual buttons on here, and you can do this is a Raspberry Pi header. So I can hook this up to a Raspberry Pi, attach a debugger to it, and debug the software. Whereas unfortunately with this guy, it has USB and software, which means if you're working on the USB software, as soon as it fails, it disconnects.
Oh no.
And that makes it very difficult to do anything with, really.
Mm.
And so all of the bootloader and everything was developed on this, while in tandem we were working on the production line for this. And as you could see, there were many mistakes that were made along the way. Um, Most notably, in addition to, so the issue with the drill that you saw is actually the finished boards, and
Mm.
it took us 8 attempts to get there. Um, so unfortunately, FOMO was delayed for, I think it was 8 months, because every time you do a PCB, it tends to take about a month to do properly. Because what happens is somebody goes and they inspect it. They go from your Gerber files to actual mask sets. Then because this was a 4-layer blind buried via board, they ended up having to essentially produce 4 different PCBs, glue them together, add drills at 2 different steps,
Mm.
laminate the whole thing, I don't remember this. There's no silk screen on this. That makes that step easy. Um, and then gold plating. So these are actually hard gold plated because USB is supposed to be gold plated.
Mm.
And what was going wrong was every time they did the hard gold plating process, which is where you put it in an electrode bath
Mm.
and you hit it with high voltage or high current, um, it would short. So you could see the USB
Oh
pads
no.
are very close together, and they would actually um, short out. And so they'd have to scrap the whole thing. And this happened 8 times or 7 times. We ended up switching PCB vendors. The new PCB vendor failed once. Um, the second time they got it. So if you need, I'm going to do a shout out to King Creddy here. He's they're the board vendor that we go to in China, and the guy loves PCBs. Like he'll do all sorts of really weird things. Um, I know the Media Lab, the MIT Media Lab, did a thing where they sent some students over, and they were doing PCB art projects. And somebody said, "Well, what happens if we put, I don't know, go out to the parking lot and get a leaf? You know, just laminate a leaf in between two layers of PCB. Can we make it like a piezoelectric element?" The guy's like,
What?
"Sure, let's see what happens." It wasn't that interesting, but the fact that he's like, "Okay, let's try this. Like,
Yeah.
I'm game. You pay for it, but I'm game. As long as it doesn't damage the machines, and if it does, you're going to pay for the machines. But yeah, let's try it." So he's the guy I go to for things like this, and he eventually he got it, and on the second try. And so again, if you need weird PCB things, they're the ones I would go for. Um,
That is good to know. And you mentioned that there's two sizes of the same FPGA on there. How did you choose which FPGA you were going to use? And
so
which one is it?
that's kind of the sad story. So this is the ICE 40 UP5K, which
Hmm.
is in a lot of open source projects. And the ICE 40 is picked because it has an open source tool chain. So somebody managed to reverse engineer the bitstream format to the FPGA, and then a whole bunch of projects all came together to um, uh, be able to write Verilog code or Python code even at this point, and then turn that through a series of tools into something that this FPGA can understand.
And is that the Ice Storm toolchain you're talking about, or is that a?
The Ice Storm, yeah.
Mm.
So the Ice Storm tool chain is plus Ice Storm, Yosis, uh, Next PNR now at this point,
Mm.
and LightX is the Python LightX slash MeGen is the Python section of that I was referring to.
Awesome.
Um, and so the ICE 40 was one of, I think, only two FPGAs that were in this open source toolchain flow at the moment, or at the time that Fomu was developed. And the ICE 40 that I picked is smaller than the one that's used in the tiny FPGA. He uses an HX8 or HK8X,
Hmm.
HX8K, I'm sorry, which is much larger in terms of the number of cells it has. 8K meaning 8,000 LUTs, 8,000 lookup tables.
Ah.
This one is a UP5K, which only has 5,000 LUTs. And the UP means ultra plus, and they mean ultra low power. So one of the problems is that the HX8K can actually be faster. Um, so, for example, when the USB stack was first ported from Tiny FPGA, it didn't meet timing at all. So when you have an array of LUTs, which is an FPGA, they can only switch at a certain speed. Any faster, and you're literally overclocking it. The tool cannot guarantee that it can meet timing. And so when the Tiny FPGA software was first ported to this guy, we discovered that it didn't meet timing. It succeeded in synthesizing. The tool reported, "Yep, I managed to route it," and then it said, "But you requested it to run at 48 megahertz, and I can only guarantee that it will run at 12."
Oh no.
Uh, and the thing is, that wasn't a hard error at the time. That was kind of just a warning that appeared.
Right.
And it's this really frustrating thing where FPGAs, it turns out, are really good at being overclocked about 50% of the time. And by that, I mean, if you take a bucket full of FPGAs, this one will meet timing no problem. And this one will just exhibit mysterious errors. And you
50%
have
of the
no,
time, it works all the time.
exactly 50. So this one
No.
will work 100% of the time, and this one will work 10% of the time. And
Oh.
it's all about binning. Like it all depends on where on the big wafer. Like a one from here, a chip from here will work fine, but a chip from here on the wafer will not work. And
Man.
uh, it's all down to physics. And this leads to some very unfortunate things where uh, somebody released this amazing. I think they ported fourth the fourth language to Fomu, using the tiny FPGA core and using the original ice storm flow, and they weren't checking for errors. Rather, they weren't specifying the timing that they wanted to meet, and it defaults to 12 megahertz. And because tiny FPGA runs at 48 megahertz, the issue was it worked just fine in their board, and then they released it
Mm.
to the internet, and it unfortunately didn't meet timing. So about half the people were reporting really weird errors, like it would connect just fine, and then as soon as you started typing messages, it would disconnect. And anytime you get spooky things like that, the first thing you want to check is to make sure that you meet timing.
Huh.
And yeah, because it fails in the weirdest ways. Um, so one of the greatest inventions of Next PNR, I think, in the open source toolchain is the ability to say, I would like you to meet timing at 48 megahertz. By the way, these bits can run at 12 megahertz. That's just fine. We're going to have two different clock domains.
Hmm.
Go let me know if this will work. And it will. It'll error out if it doesn't work.
That's really cool. You've been waving around this beautiful little injection molded, I believe, is it injection molded?
It
Uh,
is.
yeah, this little holder for the Tomu and Fomu.
Yep.
Yeah, there you go. What was it like creating that? Are there any caveats in that process or things you like about it?
So one of the things about um, designing, and one of the reasons why I like working with factories in factories in general, but in my case they're factories in China, is that there you get to meet people who really love what they do. And a project such as Fomu, Tomu, Qomu, I couldn't do it all by myself, and I rely a lot on them to help me out. So generally what I do, when you design a circuit board, you don't go into KiCad, for example, uh, design everything in the schematics, turn it into the PCB, then print it out yourself. Some people nowadays do uh, etch their own PCBs, but that's a very long and complicated process, and it's difficult to get more than two layers. So
Right.
you always have to rely on somebody else. And there comes a point where you it's impractical to do everything yourself. You have to rely on other people. And the plastic case is a classic example of me relying on other people. Um, so this was built using um, uh, FreeCAD. FreeCAD was the software that I used to design this case. One of the nice
Hmm.
things about FreeCAD is that it can actually import KiCad documents. So
What?
you can
No way.
open up your you can open up your board in FreeCAD, and as long as there is a step file for each component, which oftentimes there is, it'll give you a 3D representation of it to scale. It's called KiCad Step Up. It's really amazing, and it's great for getting like this really weird shape of the board because it has this it's rounded and it's got
Hmm.
this hole. Um, so it was great for getting something that is guaranteed to be size accurate.
Huh.
And then from that, you just use FreeCAD to build the thing around there to add. You could see gaps for components like here.
Yeah. Because it's
So
not just a flat thing. Like every little chip and transistor or whatever on there has its own little bump in the case.
yeah, its own little pocket.
So cool.
Um, and we did that because plastic has tolerances. So you can't make plastic too thin, otherwise it forms gaps. In this case, is actually particularly interesting because this actually holds two different boards. Um,
Hmm.
so because FOMO was taking so long, and Tim Ansel Mithro, who actually got me into this project, had a deadline to meet. He did an original board, the hacker version of FOMO, um, which uses components that are more difficult to source, So everything on here has two different sources you can get every component from, except the FPGA. There's only one of those. Like there's two crystal vendors we can use, two
Huh.
flash vendors, but the original, all four SPI flash lines are wired up, so you can do quad SPI, make it 4 times faster. Um, the original incarnation of Fomu was done in a much simpler process that has no ESD protection, for example. It uh, requires only a 2-layer board. It's really an amazing example of ingenuity in board design, but it's not the kind of thing you would go to mass production for. Uh, but Tim had all these made. He had 1,000 of them made, and so I designed the case with bumps that actually match both the production version of the case and
Ah.
the hacker version that he built. So one time at CCC, we tend to meet a lot at CCC. I brought him a whole bag full of cases and said, "Here you go, try these out, see if they work." And yeah, so now all of his hacker versions have cases, and life is pretty good.
That's awesome. So in this
Uh,
tweet, you're saying that you need to harden the mold. What does that
yeah.
mean?
So I kind of got distracted earlier. I was talking about all the help that I get with China. Um, so I built the tool. I imported the KiCad PCB into FreeCAD, and I built a very simple uh, case that has all of these pockets and the basic features. It has the cavity for the PCB. It has the rails on the side. It has the peg that's in the middle, the alignment peg. The idea initially was to do like heat staking of
Yeah.
this guy. Um, and I sent this off to the factory, and they said, "Okay, this looks good, but we can make it better." So they actually added these little bumps on the side. Uh,
Oh, to sort of hold the little notches in.
so these bumps are something you could grab to
Oh
pull
yeah.
out. So they added those, and
I see those bumps you're talking about.
yeah, and directly inwards of the bumps, you can see there's a little ledge, a little overhang.
Mm-hmm.
They added those as well, and those overhangs are somewhat interesting. There you go. You can see it on the top left and the top right there. There's a hole. And these are super interesting because normally when you do plastics, you can't have any overhangs. Um,
Hmm.
and those actually aren't overhangs. They're what's called a lifter, where there's an actual peg that goes into the injection molding tool and then is used to pop out the that particular section as the whole unit is popped out of the cavity. And
Huh.
they added those. And it's really interesting that those pegs, they make the whole thing. They actually keep it from falling out. They're the snap hooks, but those make it completely impossible to 3D print. Like
Right.
I tried loading this into the Form Labs Form One preform software. It said no, there's no way. I
Oh.
can't. No, you can try, but no. And it yeah, this didn't print out at all.
Hmm.
It's so sad, but it makes great injection molded plastic, and I couldn't have done it without them
That's so
um,
cool.
adapting this. So I sent them this step file, and by the way, FreeCAD is amazing software in that I think it's one of the only pieces of open source software that deals with step.
Hmm.
So when you do 3D printing with an SLA, a PLA type printer, normally you deal with STL files, which is where you take a 3D model and you slice it up into a bunch of different layers that then gets sent to a 3D printer that way. Step files are actual physical geometry. There's some color data, there is shape data, there's group data, there's names. So, for example, when I take my file in FreeCAD and I export it as a step file, he can actually see on the other side that this particular pocket is named Spy Flash Pocket.
Ha.
And he can take that and import it into his and then modify the geometry on his side. So he does that and he adds these little features, these widgets, these bumps, the holes and things like that. And he sends me back a step file that I can then open up and verify that it is good. I could see it. I could try and 3D print it and have the software throw up, uh, but I can have a dialogue with him at that point. And once I say, okay, great, they actually send it to a 3D printer they have there who somehow magically is able to print it. I don't know how they do it. The snap hooks still don't work on their very expensive 3D printer, but it does. We can verify that the fit will actually happen. And then at that point, they cut steel. So they take this big chunk of steel, which costs $3,000 or $4,000 because that's what steel is on the market,
Oof.
and they use what's called wire EDM, electro deposit
Ooh,
machinery,
yeah.
which is really pretty.
That stuff
Uh,
is so cool.
yeah, it's you go to one of these factories and there's vats full of really corrosive liquid and high voltage going everywhere. You feel like you're in a workshop. It is amazing.
Yeah, it stands for
And
like
that
electric discharge machining or something like, right?
Yeah,
You
yeah.
get those tight fitting pieces.
Yeah, I mean that's what you need because this is I think 0.1 millimeter accuracy.
Whew.
It's tight tolerances, and then they spend a couple of weeks to actually fire electrons at a block of steel to etch away at the mold. And then you get back this mold and you do one or two test shots. But the thing is, at this point, the mold is still soft. It's still pliable. You can still etch away at it. Um, but you do that test shot to make sure that it is that the fit is fine. Because normally when you inject plastic, as it cools, it shrinks, and so you actually have to make the part bigger than it's going to be at the final part. And you need to make sure that you predicted correctly how it'll shrink.
Hmm.
And the models are getting pretty good at this point at determining how it might shrink, but you could still be wrong.
Hmm.
And with a very complicated piece, it could be that you got the math wrong, or the plastic that you're getting from this particular supplier isn't behaving like
Uh,
it should. So they do a test shot where they do a few pieces, and once they decide that it's good, they then take the mold and they put it into a giant oven and they bake it, and that's called finishing or hardening. And at that point, the tool is super brittle, and it's good for I think these are rated for 200,000 shots. So we could actually make 200,000 or so cases now without needing to pay again.
hmm. Which is part of why, of course, you get things like Kickstarter, where like the cost to make the mold in the first place is sort of this huge hump that you have to get over. But once you've got it, you can do a ton of huge run.
Right. And the great thing is, so when we did Tomu initially, Tomu is the ARM-based. It's a Gecko Cortex M0. That was Tim's original idea. Um, there you go. It's the original logo. It was a small USB uh, based ARM computer. It had 8K of RAM. The initial one didn't even have a case. And when you did crowdfunding for Tomu, we actually had a stretch goal of doing a plastic case. Um, so when we got to a certain point, if we made a certain amount of income, one of the stretch goals was we were going to make a plastic case. And we hit that stretch goal. Thank you to all our backers.
Yay!
Uh, we hit the stretch goal and we were able to make a plastic case. Um, Now, with FOMU, there was no stretch goal to make a plastic case. It was a given. We are going to have one. And the reason why that we were able to do that is because we had already spent the money on this guy.
Uh,
Now, the way a mold works is it's actually four parts, but there's two big chunks that are what the machine uses to push and pull. It has vents for the plastic to flow in, and it is used to keep the plastic molten as it flows in. Then inside there are cores. And the core, if you look at it, actually looks like an inverse of the thing that you're making. So if you look at the core, it's got this particular one has four cavities for making this guy, and it has plastic runners for the plastic to flow in. Now, one of the nice things about the Omu series is that they're all the same shape. They all fit into a USB port. They all have a notch in the same area. And so this side of the PCB, this side is always the same. This side changes based on the PCB components and layout and things like
Ah.
that, which means out of these four things that you use to make a plastic case, we only have to change one of them.
Oh, that's
And in
awesome.
fact, it's the smallest bit. And so it costs less than $1,000 to do a new core for a completely different product. So this is an example of Qomu, right? Um,
Oh, you've got it there. Cool.
yeah. So this is actually the so for Tomu for Fomu we did this guy. It's a whole different PCB. For Qomu they wanted to do it all on one. So you could see
Oh, look at
this is
that.
actually the debug section with little USB and
Huh,
uh, JTAG header. This is going to be snapped off. So
that's so cool.
let's see. There's actual mouse bites right here. So we'll just snap this area off. Um, but this, of course, has another different design. And in fact, there's a reset circuit on here that's going to be pretty tall. Um, so once again, I went through and I imported the board into FreeCAD. I added pockets for the CPU, the SPI flash, the reset circuit, the crystal, all that. And then I sent it off to the plastics factory and um, they said, "Hey, could you do those same modifications?" And initially they came back and they said, "Sorry, this won't fit because it's shorter and it's missing these bumps in the side." And I said, "No, no, I know. Can you add those? And can you quote me to do the tool to you know, produce plastics for this new board design?" And we're going to be getting plastics for, we already have the 3D print test shots for Qomu. And now we're going to say, yeah, go ahead, start it, do plastic production, produce 1,000 cases. So now we'll have a separate core for Tomu, Fomu, and Qomu. Whereas the base is going to be the same for all of those as well. And so by reusing the shape, we're able to produce new PCBs with new layouts for less than $1,000.
That's amazing. And you do have so many of these. I was trying to scroll through them a little bit before. You've got Fomu, the Tomu original one that we looked at as well. Qomu. What's the deal with this one?
So
What is the Q for?
it's from Quick Logic is where the Q comes from,
Ah. I was
and
thinking
they're
like a
interesting.
quantum FOMO, but that doesn't really make sense yet.
Oh, that
Maybe
would be
50
cool.
years from now.
Yeah. No, so Quick
Okay.
Logic is interesting. So with the Ice 40, the Lattice Ice 40, that was reverse engineered by the community, and officially Lattice doesn't support that tool chain.
Mm.
Whereas with QuickLogic, the Qomu, that is actually supported by QuickLogic. They have a fully supported open source tool chain, and they're the first FPGA vendor to do that. Which shout out to them for being amazing.
Yeah.
Um, Also, the Qomu is a Cortex ARM Cortex microcontroller M series with an FPGA, with a very small FPGA. Um, with the idea being with FOMO, we only had 5,000 or so LUTs to work with, and about 2,000 to 3,000 of those were dedicated to a CPU, which means you now have less to work with. And so with Qomu, the idea is you have a dedicated CPU in there that you frees you up to be able to do other things with the FPGA.
Hmm.
Um, and so the two um, benefits of Qomu, the two selling points, are that it has a CPU and an FPGA built in, and it's supported by the vendor in terms of toolchain support.
Amazing. So I wanted to show everyone there's one coming up with solo keys for two factor auth, which I think is an amazing application for this. You've got Womu, whatever that is. Oh, it's made by Femto. Interesting. Oh, it's got a little wireless USB 32. That's super cool.
Yeah,
And a
they
little
managed to fit
Bluetooth
that in
guy.
there. Yeah. Yeah, Somo is interesting. They actually did their own case, and they are an actual secure microcontroller on there. I mean, the whole idea behind the original Tomu was that uh, YubiKey and family are all very expensive, particularly for an Australian such as Tim. So he
Mm.
decided to make one for $10 BOM cost. And the thing behind that one is it's not secure. It's not a chip that was designed with security in mind, and so you can pull out the
Ah,
keys as long as you have it. But Somu is an actual secure enclave on a chip in the form factor that fits in your USB port. So that's why Somu is
that's really
uh,
cool.
important. Yeah. So it's a
Uh,
great little family.
I've actually got a little solo key right here. I wonder if they're going to do one of these stretchy little rubbery silicone type cases as before. You said that they're making their own case, and that's what it made me think of. But like that actually wouldn't go in a USB port though. It would have to be something hard, right?
I think they have. I think they are using the same technology of case, except it's slips over the board.
And then you like
Yeah.
slip it off when you want to use it or something.
Yeah.
Um,
So theirs definitely is not injection molded plastic like this. Theirs is as you say, rubberized silicon.
Interesting. Is there anything that you'd like to say before we wrap up and just throw in there?
Um, so I will say it's nice to get this opportunity to connect with people. Um, 2 years ago, I did this blitz of going to a bunch of conferences. I think I actually met you a couple of times at various
Yeah,
conferences, the Risk 5 conference and CCC. I think we are at CCC Camp as
yeah,
well.
2015 maybe, or
Yeah.
last year, or 2 years ago, I guess.
Yeah,
I'm
I mean, the last conference that I went to was LinuxConf Australia in January of 2020. So it's great being able to connect with people because I actually haven't left this country or this city, same
yeah.
thing, in a year, um, and it's great to see that the hacker community continues to prosper and thrive, even though we can't actually come together and meet. And it's heartening to me to
Mm.
see all of the things people are doing and keep on hacking.
Like you said, it's amazing that we have the internet now.
It's going to catch on.
Yeah, it makes things so much better. Well, thanks for virtually hanging out with me. Everyone, thank you for watching and stay tuned. We'll put all the links in the description of this video, as always. And Sean and everyone, have an awesome time. Thank you again for joining us. It's so good.
Thank you for having me.